Okay, so welcome to class. I hope everyone had a good weekend. I got almost everybody's MPI Pi assignments. Is this thing even looking at me? No, it keeps running away. Why are you doing that? Now it's running the other way. Okay. Now it's going that way. That's fun. You silly little webcam. Okay. They all look good. Everyone did great. First things first, I wanted to go over the last quiz. So let's see here. Let's preview this quiz. All right, so OpenMP is meant for what type of architecture? This one should have been a gimme. This is shared memory. Smartphones, technically, I guess you could call that shared memory. But I don't think you'd be wanting to run these codes on your smartphone. Even though they actually probably could. They have more computing power than NASA did back in the 60s. So OpenMP uses a fork join model where you have one thread and it forks into multiple threads and they eventually join back together. All right, so now we come to the fun problems. Review the following C++ code, which is used in the next few questions. So we have an integer, we have a double, and we're going to start a parallel region with 3 threads, and we're going to make private copies of the variable a. And we fill a with then the particular thread number, and then there's this for loop, which looks like it's adding up, summing some sort of number. And then it outputs A and B. So at line 1 in the above code snippet, how many different values of variable A are there? So at line 1 here, the answer is 4. You have 3 private copies and the shared copy. So there's actually 4 copies of the letter A in there, and they all have 4 completely different values. The shared one has a -1, and then each private copy has its thread number, its rank, if you want to call that. At line 2, what is the output of variable A? So at line 2 here, we've already exited the parallel region, which means that this is now just the shared variable. We never touched the shared variable inside of the parallel region. So the output would be -1. And then line 3, what is the output of variable B? So we're doing this summation that goes from 0 to 9, summing the numbers from 0 to 9. We're running this in a for loop, and we're doing a reduction on B. And this one was a trick question, because we never initialized B to 0, which you would do in a normal serial code. And probably I should have followed all good programming practices and put that in there. But I didn't do it on purpose because the reduction initializes B to 0. Initializes all the private copies of B to 0. And that's in the documentation. And then each one adds up its own piece of the loop, and then at the end of the loop, they all get added together. So the answer is 45. And I purposely put 3 bad values that were just garbage so that it would confuse people. So now we have another one. Review this C++ code. It uses an integration technique to estimate pi. Assume n is defined somewhere else as a large integer. So we start with ID, start, end, number of threads. We have a variable pi, x, w, and then our sum. And we start the parallel region. We're going to make these 4 variables private, and then we're going to make sum first private. We have a single region, the start and end, and then we have something else with end. And we have the loop, and this is the actual computation loop. And then after this, we have this critical region. It kind of seems to be adding everything up. And we output, supposedly, the number pi. So line 1 here says, why is the sum variable labeled as first private? And the answer is that so that all private copies are initialized to the current shared value. If you just make them private, then they're just going to have garbage values because they haven't been initialized. But if you use first private, then it's initialized to whatever the current shared value is. Line 2. Why is line 2 inside of a single region? So num threads, we declared it up here outside of the parallel region. And so you'll notice num threads is not in the private directive. And so it has to be in a single region to prevent data race conditions. Because it is shared and we're having multiple threads that would want to store data into it at the same time. So why is line 2 inside the parallel region and not outside the parallel region? And the answer is because the number of threads outside is 1. Anyway, that can be a confusing bug if you don't understand that.
So you can call.
You can.
Do you get num threads outside the parallel?
You can, okay. And it will tell you there is 1 thread right now. Okay. Lines 3, 4, and 5 are a manual implementation of what? And you'll see I have 3 different schedules here. Dynamic, static, and guided. And it's a static. What we're doing is we're taking our loop, which would normally run from 0 to n, and we are chunking out each section as equally as we can to run from start to end. And so that is a static scheduling. And then what is the purpose of line 4 here? I learned the other day it may actually not be necessary, but the purpose is to handle any remainder in the loop. If n is a prime number that's not divisible by anything, then we could possibly have pieces left over at the end of the loop. So that is the OpenMP quiz. Now the other thing I wanted to talk about was the Gauss-Seidel project. What I got was pretty good. And let's open up this. So I've had a lot of questions as to what I was looking for in my scalability question. So there's 2 reasons that I could think of. I'm not an expert, so if any experts watch this, you can tell me the real reason. But here's how I see it, is that first off, we have since we're doing black, we'll do the black loop. We have the black loop that runs over all the black nodes, okay? And that ends. And then we have the red loop. Okay? Now in the Jacobi, we don't have this. We just have 1 loop. And if we were to parallelize this, which is the point, after all, the OpenMP for loops have an implied synchronization at the end of each loop. And so all of the threads have to stop right here. And then they can all go into the red loop. And they all stop at the end of the red loop. Whereas the Jacobi loop only has one stop here. And so there's that extra synchronization in there which can further serialize your code. The other reason that I could think of for the behavior of this is that if you count the total number of iterations that that Gauss-Seidel does and include that in your definition of work, then Gauss-Seidel is going to be doing this much work in parallel. Now Jacobi takes a lot more iterations, which means it has more work to do. And if we were to divide this work up amongst 10 processors, you can see that the Jacobi has a lot more work per processor, meaning it scales better. So that would be the strong scaling scenario. So the Gauss-Seidel in strong scaling scales worse. However, in the weak scaling scenario, if you look at the number of iterations that Jacobi takes to converge versus your size of your grid, it has a very exponential rise. It quickly becomes kind of ridiculous. And we've seen that with the 500 by 500 case. However, Gauss-Seidel, it still goes up, but not nearly as fast. And so in a weak scaling case, the amount of work that Gauss-Seidel does stays roughly constant, while the amount of work that Jacobi does, well, does not. And so in the weak scaling case, the Gauss-Seidel can scale better because it is able to distribute the work more equally between the processors. And so that's, I wasn't looking for those explanations specifically. I was looking for anything that showed that you were thinking about it and trying to understand it. And I left comments on everybody's project submissions for that on Canvas. Okay. So now we come to the part of the lecture of the lecture. The lecture of the lecture. We're going to put that over there. So we're going to talk about the MPI Jacobi project, which is due on July 9th. I'm going to talk specifically about passing ghost nodes. So when we're dealing with this, we have a multi-dimensional array, and we have to know if that array is column major or row major. Eigen, if you're using that, defaults to column major. You can switch it if you want. If you're doing a double pointer, oh please. If you're doing a double pointer, that is row major. If you're doing a vector of vectors, that is also row major. And so I'm going to talk about this as if we're dealing with a row major situation. So I gave you a picture in the PDF that's actually, I think, pretty useful. But let's say we have the red side, okay, and we have, we'll do black, maybe. Come on. This thing really doesn't like me. It's not that hard. So if we're row major, then in data, the memory is stored like this. It goes 1, 2, 3, 4. All right, so if you're row major and you want to communicate this row here to the processor on top, I'm not going to draw all of him, but he needs to know these values, and you want to communicate those up, then you can just send an entire row in one go. And I've shown an example here, assuming we're using this situation, okay? All you have to do is do the address of PI, I being the row you want to send, and the number of columns, obviously, 1, 2, 3 columns, and then fill out the rest of it. And you can send that entire row. You can also do the same thing for receiving. However, we have a problem with the columns. The columns are not contiguous in memory. If we're doing row major, then they go like this, meaning this node is separated by 1, 2, 3 spaces in memory. Okay? And so, how are we going to handle this? You could send each node separately. You send, okay, I'm going to send you this node, and then I'm going to send you this node, and then I'm going to send you this node. Or we can have a separate array, and we're going to pack them. We pack them all into this array, like so, and then we send the entire array over to the red processor here, at which point it takes that array and subsequently unpacks it. So there's two options, and the question is, which one do we use? So if you remember, the time it takes to send a message through a network is dependent on this equation. We have the latency time, that's kind of like your ping if you're pinging a website, plus then the size of the message divided by the bandwidth of the network. And so if you're sending a message of size n, let's take for instance we send each one individually. So we have n bytes that we want to send, and we send each byte individually. Then the total time that takes is going to be n times L plus 1 over B. Okay, that's if we send them all separately. And then if we send them all together, then the total time is n over B. And so there is a point where it is more efficient to pack everything and send that because of this. You always pay what they call the latency penalty because it's always present. And so you get n times L rather than just one n. So where that is obviously depends on a lot of things. It depends on your network, depends on how long it takes to pack things. So, because there is that time you have to spend. You have to spend packing it and unpacking it. So you have to include that in your calculations as well. So personally, I find that packing makes for easier programming in the end. So in general, it's faster to pack, especially if you're doing lots of data. And it's easier to program because you can just write a function that takes a column number, takes your data, takes your packing buffer, packs it all for you, and then sends it back to you. At which point you can then send that buffer, and on the receiving end you have an unpack function that does the exact same thing in the opposite direction. So here's the efficient MPI part of the lecture, is how we can actually communicate these and possibly speed up our implementation. So we're going to do this by using non-blocking communication. And of course, I'm going to assume row major. And then let's say this is the domain of one processor. We're going to call this the north, the south, the west, and the east. Okay. And since we're row major, we are contiguous in this direction. Okay, we have contiguous rows. Okay, so here's kind of a general algorithm of how we can send and receive our ghost nodes. So the very first thing you want to do is start your non-blocking receives for the north and the south nodes. So you're going to say, I'm just going to say, we're going to be receiving some data from the north and the south. At which point then we can do our sends. We can say, okay, let's send this row to the north and let's send this row to the south. So now you're going to start your non-blocking receives. And we're actually going to have a separate communication buffer for the west and the east. Okay, so you're going to say, okay, we're going to receive some data into here, and we're going to receive some data into here. At the same time, we're going to have also a send buffer. Draw that here. And we're going to start packing our values into our send buffer. So once those are packed, then we can start the non-blocking send. So we're actually going to send these two buffers. And I haven't mentioned this before, but it is possible to match a blocking send with a non-blocking receive. So if you know that you're just going to be waiting for data, then you can say just block and wait for it to show up, rather than doing a non-blocking send. So we start the non-blocking send, then we wait to receive. So there's a specific order to this. We wait to receive these nodes here. Okay, once we receive them, then we can unpack them back into our main array. Then we can wait for the north and south sends and receives, and we can wait for the east and west sends and receives. Now, the reason this is efficient is because we start our receives and we start sending our north and south ghost nodes. And we don't have to wait for those to happen. While that is going on, we can then pack the east and west send buffers. So this is the calculation part. So we can communicate our north and south and do our packing work at the same time. And we hope that our unpacking is done while everything else is being sent and received. Note, we have to take note that whether the packing/communication actually happens at the same time, whether it is actually asynchronous, as it's called, is completely up to the hardware and the MPI implementation. However, the book does give a test in section 10.4.3 that it's a full-blown program. It's like this big. You can write it up and actually see if it works. And it shows that some of them do, but most of them don't, actually, unless you flip certain settings and get into all the nitty-gritty technical details. So if that's the case, then why do we care? Well, one, it's easier to program and avoid deadlocks. Two, sometimes hardware can send and receive messages at the same time. And so it allows us to utilize that hardware to its full potential. And three, it allows the MPI implementation to do its optimization magic by saying, here's a bunch of stuff that needs to happen. Go figure out how to make it happen. Now, it is possible to get around the fact that many MPI implementations do not do this at the same time by spawning a separate communication thread. And you can use OpenMP for this. You can use another threading library. And you'll say, okay, your job is to handle all the communication, while this other thread, he's going to go off and actually do all of the calculations. So chapter 11 has a lot of details on that. I'm not going to go into it in this class. Other important things to note, network contention. If you have a ton of data all flooding the network all at the same time, you get lag and your video starts being funny, and you and your roommates are all trying to watch Netflix all at the same time, and your wireless network is just like, I can't do this. That is a problem. It's not a problem we're going to worry about because it's a complicated problem. That's why. If you know the topology of your network, you know the hardware, how it works, and all this other fun stuff, you can write your program to work around this or to work with the network. And if you can, you should always use collective calls because they use special networky algorithms, send-receive patterns to avoid network contention. And the example they give in the book is MPI reduce. If you think about it, how would you do a reduce? If you're trying to send data to processor 0, you could have processor 0 just set up a bunch of receives and then send all the data from one right after the other. This is actually really bad because you're sitting there waiting for each processor to come in a row. And so what they say instead is, well, let's have this guy send his data here, and he'll add it up, and then send it there, and he'll add it up. And they can do other fancy things that reduce the amount of communication that is done. So anyway, that is the end of the efficient MPI implementation. So anyway, please email me, ask me questions. I want to talk to you. I want to help you. So any questions from the two of you that are here? Okie dokie then. We will go ahead and stop